Welcome to In 5 Minutes. In this video clip, we will discuss second application of multi-rate signal processing, which is in interfacing digital systems with different sampling rates. Let us first of all try to understand what does this mean. In practice, we frequently encounter the problem of interfacing two digital systems that are controlled by independently operating clocks. So we basically have two digital systems which are operated by two different clocks. Now, when that is the case, all the signals in the first digital system will operate at some specific clock frequency, and all the signals in the second system will operate at some different clock frequency. So let's say we have got system A and system B. Now suddenly in some application we have to interface the two systems. That means it may be the case that output of system A is to be given to the input of system B. Now this can't be done if system A operates at, let's say, frequency Fx and system B operates at frequency F5. Whatever output we will get from system A will have the sampling rate of Fx, and hence it can't be given to system B unless its sampling rate is converted to F5. So we will need a conversion of sampling rate from Fx to F5 of the signal which is at output of system A. So analog solution to this problem will be to convert the signal from first system to analog form and then resample it at the input to the second system using the clock of the second system. Now this is something we had discussed in the beginning also. This was the first approach to carry out sampling rate conversion. However, a simpler approach is one where the interfacing is done by a digital method using basic sample rate conversion methods that we have already described. So to go from Fx to F5, we will go through the interpolation and decimation, assuming that Fx to F5 is a sampling rate conversion by a factor of I by D. We will assume rational factor for sampling rate conversion. So let us consider interfacing of the two systems with independent clocks. This is how the interfacing will look like. We have considered two systems. This is system A and this is system B. You can see that system A operates at clock A, system B operates at clock B. Clock A has the frequency of Fx, clock B has the frequency Fy. That's how system A and B are operating at sampling rate Fx and sampling rate Fy. The output of system A at rate Fx is fed to an interpolator which increases the sampling rate by I. So the output of interpolator will be I times Fx. The output of the interpolator is fed at the rate Ifx to a digital sample and hold circuit which serves as the interface to the system B at the high sampling rate Ifx. So why do we need digital sample and hold? Simply because the output of the system A will now come at the rate of Ifx, but before it goes to the second system, in which we will have decimator block at the input side, we will have to resample the signal. We'll have to convert the output to the rate dFi, and for that reason we have digital sample and hold circuit. Signals from the digital sample and hold circuit will be read at the output of the second system at the rate dFi. So you can see dFi, it will be read to the second system, but what do we have right at the input of the second system? It is decimator by D. So dFi is the input sampling rate, and if you carry out decimation by D, the output sampling rate, that means output of decimator, which is signal X here, will be having the rate of dFi upon D, and hence it will be at sampling rate Fy. So to summarize, Xn was at sampling rate Fx, output of interpolator will be Ifx, output from sample and hold will be read at dFi, and sample rate of Xm will be nothing but dFi by D, and hence that will become Fy, and then it can be given to system B because system B also operates at Fy. Interpolator and decimator will require clocks at the rate Ifx and dFi, which can be simply generated from the original clock blocks using frequency synthesis.